here, which is that these two things are equal. In other words, to a sign, if you annihilate an outgoing positive velocity photon, you get the same thing as creating an incoming negative velocity, creating an incoming positive velocity photon. So, so these two terms become equal. All right, now, we'll do that. Okay. So now what we have to do is it's easier somehow to turn this expression into that one, and that expression into this one. And because we have a isosceles formula, it doesn't possible that we can write P in K in, which is what I showed before, we can write it in terms of E in K, times 1, and then Gk in plus C bar K in. So this is P0, P1, P2, P3. 1 plus Zk in C bar K in. And then P2 is the same thing with I, and the imaginary part of Zk. And finally, P3 is the same with the 1 minus C bar squared. In other words, if we know that the photon is going to land at the point Zk, the mass of the particle will land at the point Zk, then this is what momentum must be. And similarly, we can do this formula down the formula, extension for Q, which is exactly the same, except for Zk, the E in K replaced by omega, and Zk in replaced by Z, and similarly for Ts. And then, if you do that, all these P's will disappear. Notice that the E will cancel. And if we go, well, we do all this as an algebra, I'm not going to do it on the board, but what we find, and then we get to take the difference of these, you get to add these two terms, multiply by 2, to make it look like what's up there. So with all these substitutions, this formula, the standard photon theorem in a standard Planck form, reduces to the word identity that we derive from invariance word identity that we derive from invariance under large gauge symmetry, or equivalently the matrix element of the charge conservation law. Okay, so this establishes, in a minute I'm going to go, actually, we'll take a break, but in a minute I'm going to talk about how you get this formula out of Feynman diagrams, but this is kind of a central result. We've connected the Low-Weinberg theorem with this story about infinite number of conservation laws. So let me pause there for any questions. Okay, so I took a special form of epsilon, and that was a trick to make this formula true for any epsilon. But it's not very hard to show if it's true for that special form of epsilon for any W. I wrote that as 2 epsilon, 1 over Z minus. If that is true for any W, then just a few lines to show that it's true for any epsilon. So effectively, taking epsilon equals 1 over Z minus W is equivalent to taking out an arbitrary one. Yeah. It's just tedious algebra. I couldn't let you do it. Almost as if it was shit. But I set of results there. And, there's a couple of just to spell out your conventions for Feynman diagrams. I don't want to do that. So, now, formula are true in a standard set of the 2s and the 5s and so on are correct. And so on the standard set of conventions. And in the very papers on the subject that folks spelled out, I don't want to spend a lot of time on the factors of Feynman. Diagrams. Now, so what is the basic idea? Yeah. Well, the basic idea is, what does this formula say? Derivation, one derives it. Let me erase the omega here. This is the form that you'll find it in. And perhaps one would write it without a limit here and just state that this is plus. This is a pole in Q. And this is a statement which is that this matrix element is equal to the original matrix element plus corrections, which are ordered Q. So the pole is the leading term. That's the way we talk about in Feynman paradigm. So the statement is this. Let's take any scattering process with some incoming and some outgoing particles. And then let's outgoing photon, which I'll denote by wavy line, with momentum Q. So this has momentum P1 in, Tn. And then we have P1 out, Tn out. I've only drawn 2 in. And then we add another outgoing photon with momentum, another outgoing particle. So in fact, I'm just going to derive this one for an outgoing photon. And the ingoing case is similar. And now we want to compute a new scaling amplitude, but only in the soft one. We're only interested in the soft one. So I can write that as a sum of terms. There's 2 kinds of terms. And so that photon could attach to an external line like this, or it could attach to an internal line, and it could attach to any one of the n plus external lines. So it's terms like this, where I attach somewhere to an internal line in the Feynman diagram. And this, of course, is equal to the sum of an infinite number of terms whose detailed form depends on what I even said now what theory I'm talking about, because it becomes photon. That's why the beauty of this thing is it applies to every theory with a photon in it. Okay, so in this 5-particle scattering process, there would be 4 more terms like this. Now, how do we think about this? Well, the rule for computing Feynman diagrams is you start out by computing the Green's functions, the time-ordered products, and then using the Feynman Maxwell description, and then you amputate the internal legs. So Feynman diagrams, of course, we have rules for vertices. In particular, we have rules for the photon propagator. And so what happens when I add the extra photon is, since this part and this propagator are amputated according to the LSD reduction procedure. All I'm doing is adding this propagator here and this vertex here. Right, so the difference between this diagram and the diagram without the external photon is just this propagator here and this propagator here. So now I have to say a little bit about what the interaction is. Well, let me take the interaction to be equal to the interaction with the linear photon is equal to the gauge field AA contracted with the current JA. And for a scalar field of charge Q, JA in our conventions, where the E's are all in, I've taken the factors of the electromagnetic constant E, and I put them all into the F squared, 1 pi star E, so there's no B's in the interactions here. So I have IQ phi dA phi star minus phi sub dA phi. And for a plane wave, this is just 2, and the 2 comes from our normalization in some conventions at single particle state. For plane wave, this will just be 2Q dA. This is the electromagnetic current associated with the charge Q scalar field phi, meaning under gauge transformations it goes like e to the IQ epsilon. And moreover, epsilon, we want to take the polarization of the photon epsilon to obey epsilon A QA equals 0, where Q is this momentum. So, okay. So if this has, let's say this has momentum Q, and this has momentum T. So now we need to work on 2 factors. And so what will we get Well, first of all, we have this propagator here, and the propagator there gives us a vector of minus I. So we're taking a particle of mass m. So unlike in the discussion, this is also another interesting feature. We proved that so far we've only proven this. Or later on, we're going to generalize the case of massive particles, and the proof is qualitatively different for massive, in the asymptotic description, it's qualitatively different for massive and massless particles. But in the standard proofs of the salt theorem, they're actually mostly interested in the massive particle case, but it hardly matters at all. I mean, the mass doesn't even really appear. So we have p squared equals n squared, and for a massive particle, we could be taking n squared equals 0 here. And so then this propagator here, the extra thing that we're taking, in some conventions, this momentum here is going to be p plus q. That's true in any convention. But in some conventions, the propagator is minus I over p plus q squared minus n squared. That's the propagator for a scalar field. But that, of course, is equal to minus I over p squared plus 2p dot q plus q squared minus n squared. Just expanding the square. So p squared is 0. It's a photon. This is an on-shell scattering amplitude. So all these external lines have to be on-shell. So q squared is 0. P squared is equal to n squared. And so this just becomes equal to minus I p dot q, 2p dot q. That's the propagator factor. What is the vertex factor? Well, first of all, I get a factor of E from the fact that my mode expansion in terms of normalizable one-particle states, in the formula that you derived in the homework, there's an E in front of it. In more standard conventions where there are no E's in propagators, there would be an explicit E in interaction. But, okay, Lagrange under Filmer definitions. So it's E, and then A, of course, is proportional. AA is proportional to polarization. Epsilon A. So we get epsilon A contracted with JA, which is 2QPA. So that is the vertex factor, and there's also an I at the vertex. E to the I has interaction. And so I now take this, multiplied by that, the 2's cancel, and there's a Q there, so the J. So I just get E, Q, epsilon dot P over P dot Q. The I's multiplied by 1, and the 2's cancel. That was supposed to be my big Q, yeah, okay. Okay, so but now I can take this, and obviously I get one such term for every outgoing particle. So I have the sum k equals 1 to m, pk, pk, qk, that's it. Now, and then for the incoming particles, there's a minus sign, and I get k equals 1 to n of e qk epsilon dot qk over pk dot q. And these are out, and these are in. Okay, so at the end of the day, if I just consider these diagrams, all I do is multiply the S matrix element by this funny factor, which you may recognize as the same, sometimes called the salt factor, which you may recognize as the same thing that I've written over here. Now, I haven't included everything because what about these extra terms here? Well, the point there is that the internal propagators are never on shell. They never have p squared equals n squared. So I don't have this cancellation here. And if I take q to 0, the difference between p squared and n squared will dominate, and I won't get a pull. So these diagrams are most certainly non-zero, but they don't contribute to the pull. So I could just forget about this. So that is an extremely simple derivation, and up to some times you get the same thing if you have a salt incoming photon of the same formula. Now, so any questions about that? Now, an important feature here of this formula, which had provided some alternate derivations of it from the Feynman diagram point of view, or in this form, is that we would like this defines the polarization vector only up to shifts of epsilon by q, because q itself is 0. So the physical scattering amplitude with a salt photon should not depend it should be invariant if we shift epsilon by any multiple of q. So it's interesting to look at what happens to this salt factor. Well, if we shift this by q, if we shift epsilon by q, this p dot q cancels this p dot q, and we just get that it equals the sum of over k, e times qk out, this will say out on it, minus the sum over k, e qk in. In other words, charge conservation, global charge conservation, guarantees that this salt factor is gauge invariant. And that can be used to, well, that was used, I think, really, that was Paul Lowe argued for this, Francis Lowe argued for this formula in 1958. Okay, now, I've only worked it out here for a scalar, for the case of a scalar, If you do a fermion or some other kind of charged particle, it's a little more complicated, but it works out to be the same thing. And the fact that it has to work out to be the same thing in this language, I mean, it's some work to do it. I don't think Weinberg did it in his original paper. The fact that it has to be worked out to be the same thing can be seen one way seeing it is the fact that this is the only formula that is invariant with the right dimensions and so on that is invariant under these shifts of Q. Shifts of F1 by Q. Okay, any questions about that? Okay, so now, mostly I'm deferring the discussion of gravity, but this is so short and simple that while I've got this on the board, I'm also going to, as Weinberg did in his original paper, derive the soft graviton theorem. So, I don't need to rewrite these diagrams, but because I can just say that this is a graviton of momentum Q instead of a photon of momentum Q. And then I need to know what the interaction is. So let me write interaction as interaction is equal to a half kappa HAB TAB, where for a scalar field, KAB, this is how the graviton field, which is replacing the photon, HAB, and here, this field is normalized so that there's no kappas. So kappa is the square root of 32.5 Newton's constant G. This field is normalized so that there's no factor of Newton's constant or kappa in its kinetic term. So the interaction vertex becomes like this, where TAB is just equal to TA phi dB phi minus a half TAB phi squared. And I have a graviton with polarization so that HAB is S1 Q, and it has polarization S1AB, and S1AB QB is equal to 0. That generalizes this formula. And now I have the same arguments that I need to multiply the propagator. So the propagator contribution is exactly the same. The extra propagator that you get is exactly the same whether you have a external photon or external graviton. And so I get a minus I over 2 P dot Q. And so these 1 over P dot Q, these poles, which become these moment poles when we go to momentum space, are ubiquitous in the soft theorems, whatever kind of soft theorem we're discussing. But now I have to have something different on the top because I have a different interaction term. And so what does this interaction give me? Well, this thing here just becomes 2 PA PB, and the GAB will contribute because this should also be traceless. And yeah, I did write that down. Transverse and traceless, S1AB, AAB is equal to 0 for GAB. And so I get a kappa, explicit kappa, and I get PA, PB, I get this 2, cancels to 1/2, and then I get HAB proportional to S1AB, and then I get an I, cancels to minus I, and so what I get finally is kappa over 2, S1AB, PA, TB, and again, if I had in and out particles, I would have a sum over out minus a sum over in of PA. I can't write it that way. So this is just for one particle. So more generally, if I have n incoming and outgoing m incoming particles, I get a Slav factor which is kappa over 2 sum k equals 1 to n tk out a TK out B, S1 AB. This factor is the coupling of the minus the similar term within the coupling of the graviton to the stress energy particle and divided by TK out B dot Q. So I get a very similar working formula where S1PT replaces S1 in the gravity case, replaces S1P in the gauge theory case. And just like in the gauge theory case, I also can't get poles by coupling to internal lines. Okay, alright, so my next subject, which I don't think I want to start with 5 minutes left, is to go back and understand from the asymptotic point of view what we should do when we have massive particles. So let me just point down and see if there are any questions. Oh, sorry, one more thing I want to say about this. Again, what happens if we shift, we should be able to shift Epsilon, like Epsilon AB goes to lambda A, any function of Q, times QB. That would be gauge invariance in the gravity case. And again, if we do that, we can pull the lambda out front, and we get TK, let's shift this guy, so this TK dot Q shifts, cancels with that TK dot Q, and the whole thing becomes lambda A contracted with the sum over out, sorry. So the whole thing, if I shift by Q, I have this lambda A, the sum of P over K, TK out, minus the sum over K, TK in. So the P dot Q is canceled. Now, this is just overall energy momentum conservation. So again, the consistency and gauge invariance, so we thought that the consistency and gauge invariance of the self-photon theorem in a particular form of the self factor was required by gauge invariance. Well, gauge invariance, and together with charge conservation, of course, are related to the point, imply the consistency of this formula. And here we see that energy momentum conservation, global energy momentum conservation, is required for implies the consistency of the self-photon theorem. And there's also, to answer some question about superrotation, there's also angular momentum conservation. And there's another self theorem that we'll talk about later that is related to global angular momentum conservation. So, any questions? Yes. Yes, this also looks like a word identity in a Carl CFT, and the one that is related to superrotations, and is the stress tensor, the word identity for the stress energy tensor in a Carl CFT. But those statements haven't been as fully investigated as the one for the U1. More questions? Okay.